Greetings! Here's part 4 of our series on assembly language or machine language programming using the Motorola 6800. Last time we ran a couple of example programs utilizing the trainer, and we saw what they did. But today, let's go into the simulator and have a peek under the hood. Okay, let's run the first program, the one that turned on all of the segments in the display, but run it in simulator so we can single step it and look at it and see what it's actually doing. First, let's make sure that we reload RAM. Then we set the program counter to 0, which is where the first program starts. And immediately we see a new instruction that we haven't encountered yet. It's the JSR instruction, which stands for jump to subroutine. And you will notice the jump part of it, we actually have a 16-bit address encoded into the instruction. It has 2 operands. Unlike the branch, which is a relative branch, where the offset is encoded into a single byte, and it lets you go plus minus 127 from the location of the branch address. This one is an absolute jump, and it actually tells you where to jump. But it's a jump to subroutine. So what that means is it will jump directly to this address. Very easy to hand assemble. But what it also does is it saves the return address. The return address is just the next instruction following the JSR instruction. It will save this address on something called the stack. The stack is a special memory area that is supported by instructions on the 6800. So instead of you having to maintain temporary memory locations where you save addresses where to return to, this does it for you. It will save the return address, which is 3, on the stack, and then later on when it wants to return, executing a single instruction, which we'll see, it's called RTS, return from subroutine, will retrieve that return address, put it in the program counter, and come right back here. But let's see it in action. This tells us that our stack pointer is at EB, pointing at EB. So let's set the memory window to E0. And what this is saying is the stack pointer is pointing at this location. So now let's see what happens when we execute this instruction with F11. We jumped to the address that was encoded in the instruction. But if we look at the stack, it automatically put the low byte, it pushed the low byte on the stack, and then it pushed the high byte on the stack. And now the stack pointer says E9. So the stack pointer always points at the next available free byte in the stack. Great, so we know where to go back to when we're done with all of this. Now the first thing it does over here is it saves the X register at memory location EC. And the X register contains CB, 00CB. And again, we can see that in the same window. Now this is not a push, this actually stores it, so it will store it at that exact address, but it is storing 16 bits, 2 bytes, because X is a 16-bit register. So if we look at EC, which is over here, and it's funny because it already contains 00CB because I probably ran this before, but what it is doing is when we execute storex EC, it puts 00CB at memory location EC and ED. Now we load X, and it's Remember, this is an immediate load. indicated by the pound sign of a hex number, C16F. So now if we look at the index register and we execute that instruction, it now contains C16F, just as we told it to. We store that value into location F0, which also conveniently is on the screen. So now this should turn into C16F, which it did. And now what we're doing is we reload the X from EC. So basically all we did here was we saved the value of X, and over here we're restoring it. So EC should go back to what it was before, which we know is OOCB. So execute that, and X is restored to its former value, and now the aforementioned return from subroutine. And again, in order to analyze that, we look at the stack pointer, which is pointing at E9 here. Now, it performs two pop operations from the stack. The first one retrieves the high order byte of the return address, and the second one retrieves the low order portion of the return address. Remember, the stack pointer always points at the next free location for a push, so when you're pulling, it will decrement the stack pointer first. So this RTS instruction will do all of that by itself. It'll pull 0003, put that into the program counter, and put that in the program counter. And that's basically what a jump is. It performs a jump because a jump says modify the program counter. It's not so much physically jumping, but it's changing what the program counter is pointing at, so the next fetch the processor executes will come from that address. So now we say RTS, it should go to location 0003. And it does. It just returned. If we scroll up a little bit, we'll see that's exactly what we wanted. Now what it does is it loads a 1. We're familiar, branches unconditionally to E, and does another JSR. And let's just say we don't really want to step through. This is in the BIOS code or in the firmware, and we're not really interested at this point exactly what it does. Let's just observe what it does. So what we can do is now we get into why there's a step over and a step into. Step into will execute the current instruction, F11, which we used. If it's a jump, it'll actually do the jump. If it's a JSR, it'll do the JSR, whatever. However, if we use step over says that if you're on a jump instruction, go and execute it and come back to the next instruction until an RTS is executed. So now instead of using F11, we use F10. We end up at the return address. And now several things we need to notice. First of all, what we did is we turned on one segment in here. Now why didn't it clear the display? I mean, it changed the first digit only, but this still has old garbage in it. And the reason for that is that we used, when we were in the trainer, we used the do instruction, and the do instruction inherently clears all the displays. Since we're running this outside of the simulator, it didn't do anything. It did not clear the rest of the displays. It only set the middle segment on this display. So how do we get to clear this stuff now? Is there an easy way to do it? Yes, there is. And what we're going to do is we're going to go, and this is just temporary, it's just another little trick, but we're going to go to the very last instruction, which jumps back to the beginning of the program, and we're going to put a breakpoint on it, which is F9. And what that means is now when we run the program, it's going to go turning on all of the segments and then stopping when it wants to start doing the first digit again. And that will kind of clear everything for us. So it's kind of a sneaky way of doing things, but if we now run the program, we will actually see it go through one pass of showing all the segments and clearing out all of the displays. And when it's done, boom, it hits the breakpoint at the very bottom of the loop. And now we can go back up again by single stepping with F11 and continue observing what the code does. But what this bought us is we cleared the display. You will learn these little tricks as you start writing code and looking at it, and using a breakpoint is a very powerful tool when debugging. So we already looked at this. This initial JSR sets up some variables. So we're going to F10 over it. And we can now, next to execute the next instruction, we can use either F10 or F11. It doesn't make a difference because it doesn't change the program counter. So what we're going to do is load a 1 into the accumulator, which we can see in the register window, branch forward, and this is a call into the firmware that actually sets the current segment in the current display. So we will F10, i.e. stepping over it, and we should see the first segment light, the center segment on the leftmost display. And there it is. Next, what we have is a routine very similar to what we wrote, except this utilizes a 16-bit register to allow for longer delays. And it does the exact same thing. Load X with 2FOO, we can see it in this window over here where you can see or should see all the changes occur. We decrement X and it does a 16-bit decrement. And here's our familiar branch not equal because the zero flag isn't set. The zero flag isn't going to get set till the X register is 0. Now we can single step this, and it's going to take a really long time to single step through this. Observe how the X register is decrementing. So we're going to use another feature of the debugger. And we basically we don't want to watch this. We want to get to the next instruction, which is also a new instruction. We could set a breakpoint over here. But there's an even easier way to do this, and that is if we go to debug and say run to cursor, we just set the cursor to the tab instruction. So if we say run to cursor, it'll run through the whole decrement, the delay routine, and that's what creates the delay between lighting different segments. We see X went to 0. Then there's the tab instruction, which transfers the contents of accumulator A to accumulator B. We then test B to see if A has become 0, meaning that we lit up all the segments. And on a branch not equal, because it isn't 0 yet, we go back. And now remember, we bypassed this code beforehand. Now what we're doing is we're loading the B register with the contents of location F1. And what this is the upper 4 bits, or the upper nibble of this location, contain the actual display we are manipulating. And so what we do, no, that's wrong. This is actually which segment we are manipulating. So we add 1 to it, which will step us to the next segment. Store that back in F1, which we can see over here. It was at 5F. It changed to 6F. Now we do an arithmetic shift left of A, which takes the A register and shifts it left bit by bit. So that becomes a 2. Just imagine all the bits getting shifted to the left. And see, this is when you have to think in binary. It doesn't make a huge amount of sense when you think of it in it isn't intuitive when you think of it in hexadecimal, but if you had a string of zeros and ones, it would make perfect sense because bit 0, the lowest bit, just jumped to bit 1. And now we get back to E, which puts the newly calculated display segment value into the display. We'll step over it, and we see the next segment light up. We go through the delay loop again, and we continue doing this until all of the segments have been lit up. So now we get back to the point where, remember, we tested B, and as long as it's not 0, we go back. That means there's more segments to light up. But now what we want to do is set a breakpoint on this instruction, because this means we have just completed the first digit, and we now need to move on to the next digit. So we just run it. We will see it complete its first thing, and then boom, stop when it's done lighting segments on this one. On this one, now what we are doing is we are changing one of the firmware. I mean, the firmware actually fetches which digit to go to from this memory location. Load A immediate 1 puts a 1 into the accumulator. Load X FO looks at the value in FO and loads that into the X register. Then what we do is we check to see if we have reached the last digit. So this is also a new instruction, compare X. So what we're doing is we are comparing the contents of the X register to an immediate value in hexadecimal. And if that value is not equal to it, we take the branch and start doing the whole thing for the next digit. And you will see we keep stopping on this one when a digit is done. And now if we remove the breakpoint from here, again, we can see it do the remaining 4 digits and then hit the breakpoint over here, which says start all over again. And there you go. So let's say we ran our first semi-useful program because it actually gave us feedback. Running it in the simulator, we could actually tell whether it was running or not. And now, of course, the last thing to do is to take off the breakpoint that happens when the last digit is completed and run it forever and ever and ever. There are a few more example programs. Let's have a look at those. So we've looked at these 3, which are all contained in this file, but so here's sample 4 that starts at 0. Let's load that one and see what it does. Okay, so this takes the expanded message that it gave us before, but now it's scrolling it across the displays. So it shows a little bit more logic instead of just plopping text onto the displays, where it actually takes the text and scrolls it. Doesn't necessarily makes it more readable, but it's kind of cute. The next one we have is sample 5, which starts at hex 60. And we execute that one. Yeah, I was looking at this and it didn't seem to be doing anything, but this is a numbers game actually, so it's waiting for keyboard input. So you click a key to start the game, and it lights the last decimal point. And so now you click a number. Let's say we click 8. It briefly said hi, which means it's not saying hello to us, but it's saying that the number you selected is higher than the one we're supposed to guess its number, and the 8's higher than the number to guess. So let's go down to 5, and 5 is still high. So let's try 2, and 2 is low. So we're beginning to zero in on it, and 3 is the number, and we guessed its number. It's not telling us how many guesses it took or anything like that, but this code kind of demonstrates not just displaying, but also reading key input. And since this was so much fun, we can play it again, and we just have to click a key to start over. And this time, let's be adventurous and start with a high number. And that one's high. So let's go back down to 8. 8 is still high. Let's go back down to 2. Now 2 is low. 5 is low. So it must be. No, 7 is high. And 6 is the one that it chose for us. So that's this. And then we have one final example program. And that one, I forgot, where does that start? Okay, that starts at hex 4. So let's go and execute at 4. And what this one does, it's supposed to be a clock. And since it's not using interrupts, it doesn't really have a time reference. It's entirely based on delay loops. It's kind of okay. It's counting down seconds over here. But I guess this one teaches you how to manipulate delay loops till you get the proper delay that you're looking for. Well, let's have a look at the clock code, and we'll talk about instructions we encounter along the way that we haven't discussed yet. The clock code, well, it's a time clock, not to be confused with a clocking the processor itself, sitting right here, starting at 0, but remember the entry point is 4. And the reason for that is that the first 4 bytes are used as working variables for the clock program. They basically hold the time values. And you can immediately tell, looking at this, it's using the FDB directive. And what that does is it basically reserves a 1 byte of memory and is initialized to a certain value, but it's sitting in RAM. So we could jump to this, but it wouldn't execute, because when something is disassembled and shows up as an FDB, that means it's not a valid opcode. The only valid opcode in the first 4 bytes here is 1, which we saw before, which is a no-op instruction, but the others values that are in here initially are not valid opcodes, and the simulator will stop when encountering an opcode that is invalid. So we have to start at location 4. Now, an interesting point to make is that we can see that the code and data are intermingled in the address space. They're in the same RAM area right next to each other. And this is what's commonly called the von Neumann computer architecture, where you have a single address space, and we do not distinguish between data and code, machine code and data, but we have to be aware of it when we're programming it. The complement to that is the Harvard architecture, which was used in one of the early Harvard University computers, a large tube-driven beast from the 50s, and that had two address spaces, one for instructions and another one for data. So we won't get into the whys and whats and pros and cons of that, but those are the two major architectures that exist. And nowadays, looking at modern processors, it would seem that they're all von Neumann architectures, but that's not really true. There's actually a third architecture that is called the modified Harvard architecture, and that's because most of the new processors have, for instance, in the instruction pipelines, they have several caches to speed up execution. So, for all intents and purposes, they look like von Neumann architectures, but they actually are modified Harvard architectures. So now you know some new words to use when you're showing off to your friends about how much you know about microprocessors. But let's go ahead and see what's happening in this program. Again, the entry point is 4, so we should probably set our program counter to 4 and see what the code does. We jump right into a delay loop. We're doing a 16-bit load here, and we just decrement it and keep looping here. And that is an entry point that is jumped to. We can see further down here we jump to that from the middle of the code. But we already know how the delay loop works. And we don't want to sit here and step through 86,000 instruction. No, that's actually more like, oh, what is it? Take a guess. Probably like in the neighborhood of 50,000 instructions, but we will use the jump to cursor simulator command, and that jumps us ahead to actual code. Load accumulator B with 60. We already know that. So here's a new one. Set carry. There are several instructions that directly manipulate the condition codes or flags. So what set carry would do is set the carry flag to 1, but it is already set to 1. So the instruction isn't going to do anything. Another new instruction, branch to subroutine, which is a short version of a jump to subroutine. It only takes up 2 bytes, and again, your destination or your address of the subroutine is limited to plus minus 127 bytes from where this is called. Remember, in processors like this, saving bytes was very important. So we do a branch to subroutine at 1E. We load X with the constant 3. Make sure that that's what happened. And now here's a new addressing mode. We've seen the load accumulator A instruction, but we haven't seen this yet. This is called the index mode, and the way it works is the address, the source address or memory of what we want to load is made up of the contents of the X register, which is 3, and a constant offset. So what we're loading is 0, we're loading from 0 plus 3, which conveniently is right up here. And that's initialized to 21. So when we execute this, A should contain 21. Another new instruction. Add with carry to the accumulator. Now, add with carry, there's also a regular add to accumulator. We've just encountered this one first. And it just adds, in this case, the immediate value of 0 to the accumulator. Seems very nonsensical, doesn't it? Why would you add 0 to a number? Well, the reason for that is the little c in here. Remember, before we called this, we set the carry flag up here. So what it does, what this instruction does, is it actually increments the accumulator by 1. Because add carry not only adds the operand over here, but it also adds the carry flag to it. Since we have 21, we should end up with 22. Then we have the decimal adjust flag, decimal adjust instruction, which is one of the more sophisticated, if not the most sophisticated instruction in here. And what that does is, remember, if we look at a number, we need to know the base. We know that the accumulator is in base 16. So it's a hex 22, which is decimal 34. However, we want this number to contain 2 decimal digits, and that's what the decimal accumulator adjust does. It goes to this number and it converts it to 2 decimal nibbles and generates and sets a bunch of flags to let us know if we overflowed, if there's carryouts, and all of that. Now, with a value like 22, it shouldn't really do anything to this because this is actually a valid decimal number. So we execute DAA, and it is. Then we do a compare B to A. Comparing B to A essentially does, it subtracts B from A. That's what happens under the hood. But it doesn't affect any of the registers. So if we execute that, we now have all the flags set. The compare sets most of the flags to give us the results of the compare. And it says on a branch on carry set, go to 2A. Our carry is set. We have modified the number. We have incremented this number by 2, by 1 actually. And if you observe closely, you'll see that that's the number of seconds. So now what we do is an accumulator B was set to 60. So what we're doing is to see if the seconds overflowed into minutes over here. We use the store accumulator A, which we've seen before, but this time we also use the index address mode at the contents of X offset by 0, which is a 3. So see, we had 21 seconds in here. If we execute this instruction, we'll get back to it. Actually did it because we can see that this turned to 22. But the reason it messed up the disassembly is that 22 is actually a valid 6800 instruction. So it's trying to disassemble it and jump backwards, and anyway, ignore this. It is trying to disassemble and saying jump somewhere behind, jump back minus 100 locations or whatever. But really, the only thing that's salient is that location 3 actually got changed to 22. So what remains to be seen is what do we do with that number? So the next thing we do is we decrement the index to 2. There is a 3 in here, and that is most likely the minutes. And it's probably easier if we look over here in the memory dump. That shows more clearly what the values are, and that the first instruction we have over here hasn't been changed. It's just being interpreted. The disassembler does not know, cannot distinguish between data and code. Remember our discussion about the machine architecture. This is something you will encounter when simulating. But going back down to here, we decrement it, so we point at the minutes. Another new instruction, TPA. And what that does is it transfers the condition codes into the accumulator. We already know they're 11, so there you go. The reason to do that is this is another way to manipulate the flags. See, in this case, what we want to do is we want to toggle the H flag. Now we have set and clear instructions for manipulating each flag, but there's no toggle instruction. So the way to do it is we transfer it into A, an exclusive OR with an immediate value of 1 will toggle bit 0. Remember, an exclusive OR, the result is 1 if the source and destination bits are not equal. Does that work? Well, if the original bit was 0 and we exclusive ORed it with 1, 1 and 0 are different, so the result would be 1, and we've toggled the value of that flag. If the original bit was 1 and we exclusive ORed it with 1, both 1 and 1 are equal, so the result would be 0. And again, we've toggled it from 1 to 0. The flag didn't change yet, but the accumulator changed. It lost the 1, and the next tap instruction puts the condition code register back. The accumulator into the condition code register. So now we've reset the half carry flag, and we have the 10 in here. And the next thing, we return back to where we came from. Unfortunately, this is taking a lot longer than I had anticipated. But in general, what it does, it'll perform the same routine every time it increments the seconds. And if there's an overflow from the seconds, it'll go increment the minutes, and then the hours. And on its merry way it goes. We've looked at some new instructions. Some of you may have wondered why the transferring the condition codes are called TPA and TAP. P stands for processor status. Transfer processor status registers to A, and vice versa. But with all of this in hand, you should be able to look at a programmer's manual for a 6800 and be able to figure out what all of the codes do. Well, we have come to the end of this episode. I'm not going to spend more time on this. I think you're more than able now to pick up from here and start writing your own code. But we're still not done yet. Remember I pointed out that the Heathkit, you could buy an expansion box for it that had a bunch of expansions. It was a silver box that this just sat on with the same footprint, and greatly expanded the capabilities of what the base box could do. So what we'll try to do next time is add an expansion box to this, which is obviously add-ons in the simulator, and see if we can make it less cumbersome to use this thing and see how useful it may become. Thanks. Please like, comment, and do all the other good stuff, and we'll see you soon.